what it means to be symmetrical with respect to a circle. So okay. And we agreed that if Z and Z star are symmetric with respect to the circle, then that was saying that Z is equal to squared of 1 over Z minus A complex conjugate plus A, right? Because this is A and this is Z. Then as we go out along this ray, like this, okay, the closer we are to A, the more we're sent out along this ray. So this thing, oops, change color. C star should be given by this expression, because in coordinates, so in xy coordinates, what would this be? This would be saying that x star or y star is equal to squared of x y minus minus a over x minus, oops, there's no brackets around a, plus a, because when we write this expression in complex notation, this is the same as z minus a times z minus a complex conjugate, and this thing cancels, so it gives us this expression like this. Right? Everybody feeling okay with that? Yeah? All right, so the theorem we're going to prove today and then later use is the following. So, theorem. Given a circle or line which we're going to denote by C, if Z1, Z2, Z3 are pairwise disjoint points on C, then Z and Z star are symmetric with respect to C, if and only if Z1, Z2, Z3 complex conjugate is equal to this thing. So this is the statement I put up on Tuesday, and now we're going to prove it. Okay, so let's try and save space. So proof. Let's first take the case when C is a circle. So, okay, so the key thing we're going to use to prove this is the fact that we learned that this cross ratio stuff is invariant when we take Mobius transforms, i.e., so recall, if T is a Mobius, then we found out that T of Z, T of Z1, was the same as this thing. Oops. That's what we learned, right? That's the theorem the last time. So that allows us to do these kind of transformations of this cross product expression. Another thing to notice is that the cross product, let me just write out the definition just one time. The cross product which is given by this thing, has this nice property that if we take complex conjugates through this, then this is taking the complex conjugate of this thing, and that's the same as that thing breaks down into taking the complex conjugate of each part of this expression, right? Because this is what complex conjugates do. If we have A plus B, or A times B, more interesting. Well, maybe let's just do Z times W. Times W, complex conjugate is Z times W bar, right? So that when we put this thing through this, then we'll put the bar on every part of this stuff, on every expression inside this, because that's what complex conjugates allow us to do by this thing. Yeah. So this is the same as Z bar, this thing bar, this thing bar, this thing bar, like this. Yeah. And we're going to use that shortly in the proof. Okay. So I'm going to erase the board, and we're going to get to work on this. We have points Z, Z1, Z2, Z3, and we're going to take the complex conjugate, and the first thing we're going to do is we're going to act with this Mobius transform that simply subtracts A from everything, okay? Because that's a Mobius transform as well, right? So Mobius transforms T of Z is equal to, oops. So this is a different A, this is just the general form. Let me put it, okay, let me do capital A, Z plus B over CZ plus D, right? So that includes the map that just takes Z and adds a constant B to it. So I can set A to be 1, C to be 0, D to be 1, and then we're going to have Z plus B is an example of such a map, right? Cool. So this thing is equal to Z minus A, Z1 minus A, Z2 minus A, and Z3 minus A, like this. Yeah. What do we do then? Oops, I forgot to put a bar on top. Then we're going to put the complex conjugate inside this expression. I don't want to rewrite everything, so let me just put a bar here, a bar here, a bar here, and a bar here. Get rid of this. Like this. And then what we know that these guys are all on the circle, right? So we know that Zi minus A squared is equal to R squared, but that's the same as saying that Zi minus A bar, Zi minus A is equal to R squared, right? So that's the same as having Zi minus A bar is equal to R squared over A, like this. So we can replace each one of these guys with that thing. Let's put it over here. And then we're going to have r squared. Oops, z1 minus a. Like this. Yeah? Now, let's take the Mobius transform that does this, and let us do this. Let's do this. Let's do like this. Because no, let's do it like this. Because when we put these guys into this, then we are just going to get z1 minus a, and all of these guys will be nice and simple, and this thing will be turned into something else. But first, just agree with me that this thing is just a Mobius transform again, because for the right choice of coefficients, we get something like this. Yeah? So we have the right to just apply the Mobius transform to everything inside this expression, and it doesn't change the cross product. Yeah? So let's do that. So the first term, applying this to this thing, we're going to get r squared over z minus a complex conjugate, and then all of these guys gets turned into something rather nice like this. z1 minus a, z2 minus a, z3 minus a, like this. Yeah? Cool. And then finally we do the Mobius transform, which is just adding a to everything. Yeah? Which is t of z equals z plus a. Again, it's a Mobius transform, we can apply it to everything, and then we get this. And we get, I'll put it here. Complex conjugate plus a. And then here we have z1, z2, z3. Yeah? So that is this thing is equal to this thing, and our claim that we have z and z star being symmetrical is exactly saying that this is equal to z star, z1, z2, z3, right? Yeah. But what are we looking at here? So if you just fixed your z1, z2, z3, and then think of the mapping z goes to, this itself is a Mobius transform, as we discussed, right? It's a Mobius transform, and it's an invertible one. It's one of the non-trivial ones, which is invertible. So what we're looking at is that the Mobius transform given by this applied to z star agrees with the Mobius transform given by the same agrees with the Mobius transform. Start again. What we're looking at is that the Mobius transform defined by this applied to z star agrees with the same Mobius transform applied to this thing. Yeah, but they are bijections. They are bijections. So the only way that's possible is if this thing is equal to this thing. Yeah? Give me a thumbs up if that makes sense to you. Okay, cool. So this implies that r squared z minus this thing plus a is equal to this. Yeah? So that's exactly what we claimed. Yeah? So defining symmetry via so defining symmetry via the claim that z1, z2, z3 complex conjugate is equal to is indeed giving us exactly the notion of symmetry we expect. Huh? Okay, cool. Now we're going to do this for a line. So given a line, L, let us make a smart choice of points Z1, Z2, Z3 on the line. So recall the formula again for the cross product is this thing. So if we choose Z3 to be infinity, that is still a point on the line. So let Z3 equals infinity. But then this expression here when you put infinity into this, we see that that this guy is going to cancel with this guy, and all we're going to get left with is just z minus z1 over z2 minus z1. So this thing is the complex conjugate of z minus z1 over the complex conjugate of z2 minus z1. Like this. Because again, when we put this z3 equals infinity, then this is just this thing just becomes, let me rewrite this. This thing just becomes 1. So we can rewrite this as z minus z1 over z2 minus z1, and then z2 minus z3 over z minus z3. So if we look at this thing here, as we let z3 go to infinity, this thing is just tending to 1 no matter what our choice of z actually is. Yeah. So at infinity, this expression here is exactly 1. Yeah. So we just end up with this expression right here. Yeah. And the statement that z and z star are symmetric across the line is the statement that this is true. And again, we're going to make the choice of z3 being infinity, which again reduces down to this, so z star minus z1 over z2 minus z1. Yeah? So what is the consequences of that? Let me create some space. Well, if we take the absolute value of both sides of this, then what we see, we have the absolute value of z1 minus z bar over the absolute value of z2 minus z1 bar, and that's the same as the absolute value of z star minus z1 over z2 minus z1. And taking the complex conjugate doesn't change the absolute value of any complex number, right? So this thing is, oops, this is 1 here. This is 1 here. So this thing is the same as this thing. So, and let's stop writing the complex conjugate at the top here, because again, it doesn't change anything when you take the absolute value. So it's z1 minus z is equal to z star minus z1. And that's for any z1 on the line, right? Right, so what does that mean? So this is the line L, this is z star, and for any line L, sorry, for any point z1 on the line, And this distance is the same as this distance, which is the same as saying that z and z star are symmetric across the line. Yeah? Cool.